We're going to spend 3 days talking about graphing rational functions. Let's start with day one. How do I find certain things? So, first of all, you're going to be asked to find removable discontinuities, which are holes, horizontal asymptotes, vertical asymptotes, x-intercepts, and y-intercepts, and then be able to graph things. So, let's talk about each of these things. Removable discontinuities are values of x that make both the numerator and denominator equal to 0. This will put a hole in your graph. Horizontal asymptotes. This is what we call the end behavior of your function as x goes toward negative infinity and positive infinity. So these are limits, and this ended up being in the wrong spot. Sorry about that. So did this. I don't know why that got in the wrong spot too. No, stop moving. No. Okay, that's better. So we call that the limit as x approaches negative infinity and positive infinity. And math notation, we see that. It's kind of like what happened when we were doing polynomials, except when we were doing polynomials, the limits were always the function always approached either negative infinity or positive infinity. Well, now we're going to follow what's called the biggest exponent rule. If the exponent in the denominator is bigger, our horizontal asymptote will be y equals 0. So the answer would be the limit as x approaches negative infinity of f of x equals 0. Limit as x approaches infinity of f of x equals 0. That's if the exponent in the denominator is bigger. If the exponent in the numerator is bigger, there is no horizontal asymptote. It's actually a slant or an oblique asymptote, but those go off to either infinity or negative infinity. And that's an honors pre-calculus topic. We will talk about it a little bit in our class, but that's not on your test in terms of figuring out what the slant or oblique asymptotes are. If the exponents in the numerator and denominator, the biggest exponents, are equal, then the horizontal asymptote is y equals a over b, where those are just the leading coefficients of the numerator and denominator. And we'll show you examples as we move along. Vertical asymptotes are values of x that make only the denominator equal to 0. So that contrasts with holes that had both the numerator and denominator equaling 0, which in other parts of this chapter, we would have canceled off the numerator and denominator when we had a removable discontinuity. A vertical asymptote is only when the denominator is 0. This puts a non-permeable, aka cannot cross it, vertical line on your graph. Horizontal asymptotes, by the way, are semi-permeable, so you can cross them in certain situations, but vertical asymptotes, never permeable, can never cross them. X-intercepts and y-intercepts, you can write this stuff down, but basically it's the same as what we've been doing. So x-intercepts only make the numerator equal to 0, and it puts an x-intercept on the graph. Y-intercepts are what happens when you substitute x equals 0 into the function. That gives you a y-intercept. How do I graph a rational function? First, you make sure everything that we just talked about in the previous things ends up on your graph. Second, we follow the rules of asymptote behavior, which are kind of like the even, even, odd, odd dance of asymptotes. So we will deal with that as we go forward. And then we use logic and just kind of use our number sense to determine when x values give positive or negative values of the function. So let's now do 3 problems today. We'll do 3 problems tomorrow, and we'll do 3 problems the day after that. Problem 1. First of all, let's factor the denominator. So I'm going to rewrite this as f of x equals x minus 5 over 2 times x minus 5 times x plus 3. So what I notice, the first thing I'm going to look for is, do I have any holes? Do I have any removable discontinuities? There's clearly one at negative 5 because the negative 5, x minus 5, I'm sorry, not negative 5. There's clearly one at 5 because x minus 5 makes the numerator and denominator equal to 0. So if I wanted to rewrite f of x in a simpler form, I could rewrite it as 1 over 2 times x plus 3. So f of x looks like 1 over 2 over x, 1 over 2 times x plus 3 in every aspect except at 5. When x equals 5, there is no value for f of x. in this particular case. Now, if I just graphed 1 over 2 times x plus 3, there would be a value at 5. But we're talking about this function, and this function has x minus 5 appear in the numerator and denominator. So the function looks exactly like what I circled in red, except for at x equals 5. So what I'm going to do is I'm going to substitute 5 into my new red circled equation. And what I find out is I get 1 over 16. So that would be my y value. At 5 comma 1 over 16, there is a hole on the graph. So 5, and it's really close to 0, but it's positive. There's a hole on the graph. So that means that it approaches that value, but it never actually hits 5 comma 1/16. There's a hole there. Horizontal asymptote. So horizontal asymptote is what happens as the function goes off to infinity or negative infinity for x values. If I take a look at this, if I substitute in really big values for x, either positively or negatively, I'm going to end up with 1 divided by a really big number. So this is going to end up being 0. The horizontal asymptote is y equals 0. That ends up being the case because, as we talked about earlier, the denominator's power is bigger than the numerator's power. So squared is bigger than just x to the 1. Or if you look at our new function, 1, so there's no variables in the numerator, there is a variable in the denominator. The denominator's bigger, it's more important, basically, as we go off to infinity. So y equals 0 is my horizontal asymptote. So my function is going to approach that as we go off to infinity. Vertical asymptote would be any value that only makes the denominator equal 0. So that's going to be at x equals -3. Notice that if I substitute in -3, it makes the denominator 0, but it did not also make the numerator equal to 0. X-intercepts, that's any value that makes only the numerator equal to 0. In my reduced function, there's nothing that makes the numerator equal to 0, so I have no x-intercepts. Y-intercepts are what happens when I substitute 0 in for x. When I substitute 0 in for x, I get 1/6. That is just something that I can do when I substitute in 1/6, or when I substitute in 0. So I'm going to get 0 comma 1/6, and that is a filled in circle. So now I put a vertical asymptote at -3, which I probably should have done earlier, my fault. And so now I'm going to graph my function. So what's going to happen is, as I approach infinity, it's going to get really close to 0. It's going to hit 0 comma 1/6. And then as I approach my asymptote, it's going to go off to infinity. Since the power in the denominator of x plus 3 is 1, so this is like x plus 3 to the first. It's just like in the last chapter when I had a root that was to the first power, it would cross the root. And when I had something squared, it would bounce off of the root. Well, in this case, if I have something to the first power, as it goes off to infinity on both sides of the vertical asymptote, they're going to approach different sides. So my function will look something like this. And that makes sense because if I plug in any value that is less than -5, or I'm sorry, less than -3, the denominator will end up being negative. And so I have 1 divided by a negative number. All of these values over on the left side should be negative. That is how I graph number 1. When I look at number 2, I'm going to factor the denominator. So f of x is 2 times x minus 5 times x plus 4 over 3 times x minus 5 times x minus 1. Once again, I have a removable discontinuity at x equals 5 because I can cancel out the x minus 5s. So 5 is the x value of my removable discontinuity. F of x I can rewrite in more simplified form as 2 times x plus 4 over 3 times x minus 1. So if I substitute 5 into my function, I get 2 times 9 over 3 times 4. That's 18 over 12, which is 3 halves. So at 5 comma 3 halves, there's going to be a hole. That value doesn't exist. So 5 comma 3 halves, or 5 comma 1.5, has a hole in it. It's not going to actually exist. Horizontal asymptote, if I substitute in really big values of x, it ends up being 2 times large over 3 times large, and really close to the other large. So let's say I plug in a million, I get 2 times 1,000,004 over 3 times a million minus 1, or 999,999. These two values end up being so close to each other as x goes off to infinity that that's basically 1. So it ends up being 2/3 times 1. So 2/3 times 1 basically ends up being 2/3. And if I remember what I learned earlier from the other side, if, or from the other side of this page, if the exponents are equal, y equals the leading coefficients divided by each other. So what I end up with is my horizontal asymptote is y equals 2/3. That is a horizontal line at y equals 2/3. So it's slightly below 1. And that's supposed to be a horizontal line. It's just kind of hard to draw on a smartboard. Vertical asymptote is anything that makes only the denominator equal to 0. So that's x equals 1. So I'm going to draw a vertical asymptote at x equals 1. X-intercepts are anything that make only the numerator equal to 0. So I can just kind of look at this function to determine that. So only the numerator would equal to 0 at x equals -4. So -4 comma 0 is going to be an x-intercept. And then the y-intercept is what happens whenever I substitute 0 in for x. So I get -8/3 as my y-intercept. So that's -2 2/3. So that looks something like this. So what I end up with, if I graph this, is my function will hit those points. And once I get enough points, it ends up being relatively simple. Now notice again, the denominator's x minus 1 does not have a squared or anything, so that means they go in opposite directions. So as I approach this line, x equals 1, one side is going to go to negative infinity, another side is going to go to positive infinity. If I take a look at the limits, the horizontal asymptote, if I write the limit as x approaches negative infinity of f of x, that would be 2/3. Notice it's going to approach 2/3 forever. Likewise, the limit as x approaches positive infinity as of f of x, as x goes to the right forever, that's also 2/3. So I'm just showing you the mathematical notation for those. Final problem. So if I have f of x, I'm going to look at factoring the numerator and denominator. If I factor the numerator, I get -2 times x plus 2. And if I factor the denominator, I get x minus 8 times x plus 1. So what I'll notice is that there are no values of the denominator that end up canceling off with the numerator. So there are no holes. There's no removable discontinuity. Horizontal asymptote is going to be y equals 0 again, because notice that the power in the denominator is greater than the power in the numerator. So I have y equals 0 as my horizontal asymptote. Vertical asymptote is any value that makes the denominator equal to 0 and not the numerator equal to 0. So x equals 8 and x equals -1. So I have two vertical asymptotes here. I have x equals -1 and x equals 8. So if I look for x-intercepts, that's any value that makes the denominator or the numerator only equal to 0. That's going to be -2. And if I substitute 0 in for x, I figure out what my y-intercept is. So if I substitute 0 in for x, I end up with -4 over -8, which is 1/2. So I know that the points -2, 0, and 0, 1/2 are on the graph. So if I look at this function, basically what I have to do is I kind of have to figure out what is happening here. If I substitute in large values of x, so something like x equals positive infinity, the numerator would end up being -2 times a big positive number, so that's negative numerator. And then the denominator would end up being negative, or both of those numbers would be very large positive, so positive denominator. That means that my function, as I go off to infinity to the right, is going to be negative. So that's kind of what my function will look like over to the right. Now remember my rule, since the value around x minus 8 is to the first power, that means that these are going to go to opposite signs. So it'll look something like this. It'll go off to different ways going to infinity. Then I know that there's a value at 0, 1/2, so I have to hit that value. And it never crosses the x-axis there. So that means that I can't end up making it go down toward negative infinity. So since it never crosses the x-axis, it has to go back up. Since this power at x equals -1 is a first power, it goes to a different sign. It has to cross x equals -2, and then it has to go toward negative, it has to go toward 0, because that's my horizontal asymptote, as x goes to negative infinity. And that kind of makes sense, because if I plug in large negative numbers, I get -2 times a negative number, large negative number, so that would be a positive numerator. And then I would have negative large number times negative large number in the denominator, which ends up being a positive denominator. So that means that as I approach negative infinity for x, I have to have a positive value even though it is approaching 0. It is probably beneficial to show you this graph on Desmos just to show you what's actually happening. So as we approach infinity for x, it does approach 0, the function. And then we have this asymptote at 8, x equals 8. The function then hits 0, 1/2 and goes up toward infinity at x equals -1. Notice that as we approach each asymptote, it's going to the function is going to go toward opposite directions. And then we have this intercept at -2, and then it approaches a high mark at x equals -5.162 or so, and then it comes back down as we go toward x equals negative infinity. The function goes back toward y equals 0.